Hello everyone, I'm Baltazar Briere, and today I will present my work on the in situ acoustic characterization of a porous layer backed by a large air cavity. So, as an introduction to this work, I need to make a reminder for the previous work that we presented in a former conference about this topic. So we managed to characterize rigidly backed porous layer using a characterization procedure including pressure velocity measurement using the impedance gun device and model fitting procedure that made use of the Delaunay-Beasley-Mickey model. And thanks to this procedure, we were able to accurately estimate the fluoresivity and thickness of the measured porous layer. So once the case of a porous layer with a rigid backing was tackled, our next step for this research was to figure out whether or not this method could also be applied to systems where the porous panel is backed by an air cavity, which is, for example, typically found in suspended ceilings. And so that is the motivation for this research. A straightforward approach to tackle this new problem of a porous layer backed by an air cavity is to simply modify the impedance model of the model fitting procedure and using the transfer matrix approach. So simply computing the predicted impedance by computing the impedance of an air gap and simply using the transfer matrix approach to put a porous layer on top of that. Unfortunately, using this transfer matrix approach is not sufficient to provide an accurate model fitting when the air cavity behind the sample was too large. And this is because the large air cavity induces a non-locally reacting behavior of the system, and thus in the configuration of the measurements for this in situ procedure, this made it impossible to retrieve accurately enough the properties of the material. Hence, to tackle these new cases with large air cavities, we needed another approach, and that is the one I'm going to present to you today. So here is a scheme of the measurement procedure, because for this method we need, of course, to acquire some estimation, measured data for the reflection coefficient of the system. And so that's what it looks like. So we have a round sound source and a PU probe, and we position them close to basically a system that features a porous panel and an air cavity. And we would like to retrieve, without having to look at it, what are the fluoresivity, thickness, and air cavity of the system. Thanks to the PU probe, we can measure the impulse response of the pressure and velocity directly. And in this procedure, we used an existing approach where we measure the pressure and velocity impulse responses in the free field, so with the device away from any surface, and near the material surface. Now we have 4 impulse responses, and we can window them in order to remove the parasitic reflections. And for that, we use the Adrian time window, which is a very handy time window to remove parasitic reflections from impulse responses. From these 4 impulse responses, we can compute the impedance in free field and the impedance near the surface of the material. And with those two impedances and the knowledge of the probe to sample distance and the probe to source distance, then it's rather straightforward to simply estimate the reflection coefficient using a pseudo plane wave approach. And it's called the spherical to plane wave approach, actually. So we assume that the reflection on the panel is specular, but that there's still some decay that is taken into account, spherical decay that is taken into account in this equation. So now we have the measurement, an estimation of the measured reflection coefficient, and now we would like to compare it to a model. And similarly to the previous work, for rigidly backed porous layer, we're going to use the Delaunay-Beasley-Mickey model, where the characteristic impedance and the propagation constant within the material are simply estimated from the fluoresivity alone. Of course, a more sophisticated model could be used in case the porous material exhibits some more less common behavior. As I mentioned in the introduction of this presentation, it is not sufficient to simply add a porous layer on top of an air cavity in our model to retrieve the parameters. This simply does not work for large air cavities. So what we tried to do in this work was to model the whole system by simply a standalone porous layer, which means that we model the layer we model the system as simply a layer that has no backing, so that we have a reflection coefficient under this form that we can model under this form, and you can see that we completely neglect the effect that there's a rigid backing at the bottom of the air cavity. So for the model fitting itself, it's I think a rather straightforward approach that we used. So we basically used the reflection coefficient that we measured and the reflection coefficient that can be predicted using this standalone porous layer, or maybe you can call it transmission porous layer. And we simply minimize the cost function, that is the difference between the two, looking for the thickness and fluoresivity and probe to sample distance that will minimize this cost function. And from this, we extract the parameters that allow this minimum, this global minimum, as the estimated fluoresivity and thickness of the layer. However, once we have performed the model fitting and retrieved the fluoresivity and thickness, we could still potentially be missing the air cavity depth, which is not a parameter that is retrieved by the former model fitting. And so the approach we found to estimate this air cavity depth was simply by looking at the reflection coefficient that is measured, in which you can clearly see some resonance, and by taking the average frequency leap between the two consecutive peaks, we can estimate the depth of the air cavity by assuming that this frequency leap is almost entirely related to the air cavity itself, because it's much larger than the thickness of the panel. All right, so now comes the experimental validation. So for this, we used 3 different porous layers that we combined with 3 different air cavity depths. As you can see on the picture, we just simply put the porous layer on the top of this air cavity I think it's a 50 centimeters concrete floor, so quite reflective. And as you can see, those porous layers that we used have different fluoresitivities and thicknesses. So once the reflection coefficient was measured, the model fitting was performed in the frequency range of 1 to 8 kHz, and we had, of course, some research boundaries, which were encompassing most of the commonly used porous material properties that are used in acoustic in room acoustics. As for the probe sample distance, we measured it quite close to the systems, to the surface of the system, so we used from 0 to 30 millimeters. And as you can see on the figure on the right, where you have the resulting measured reflection coefficient and the model, you can see that the fitted layer model is in good agreement with the general trend of the measured reflection coefficient. However, clearly you can see that we are missing the resonance that's due to the cavity, the air cavity, which is expected since we are using only a standalone porous layer model. So now the results. Those are the results from the measurement, and I'm going to break it down for you for each parameter. Here are the results for the fluoresivity, and as you may see from this table, the maximum deviation from the reference value was about 10 kilorayleigh per meter for, I think that was for material A. And you can see that that worked for the 3 different, the three porous layer that we had. For the thickness, we had a maximum deviation of about 6 or 7 millimeters. And this was mostly for the softest porous layer measured. For the two other ones, the maximum deviation was about 5 millimeters maybe. As for the estimated air cavity depth, we had deviations of about 20 to 25 millimeters. However, this resulted in much lower relative deviations than for the other parameters because our air cavities were actually quite large for our cases. Once those three parameters are retrieved, then it's possible to use the same model that we used to perform the model fitting in order to retrieve the acoustical properties of the system and to compare them with the prediction from the reference values. And as you can see from this table, we have an interesting patterns where the error basically increases as the fluoresivity of the layer goes down. And it's very clear to see here that for material C, the error is a bit larger when reconstructing the absorption coefficient and reflection coefficient, especially when the air gap is the largest. So for a graphical representation of this error, here is the comparison of the reference value and the reconstructed value of the absorption coefficient for the material B for the three different air cavity depths that we used. And as you can see, the general trend of the absorption coefficient is relatively good. We have a good match between the two. However, you can see that at low frequencies, in this case, it's for the 240 millimeters air cavity, we can have a significant deviation in the 250 third octave band, for example. So in conclusion, a characterization procedure for a porous layer backed by a large air cavity is presented. The originality of this model fitting is that we used the standalone porous layer model in the model fitting process, which allowed to estimate the thickness and the fluoresivity of the porous layer much better than by using simply a transfer matrix approach to model the system. And the air cavity depth, D star, was retrieved not by model fitting, but by analysis of the peaks and dips in the measured reflection coefficient. The experimental validation showed that the reconstructed absorption coefficient and reflection coefficient are quite in good agreement with the prediction obtained from the reference parameters on a broad frequency range, even though some significant deviation of 0.1 can be found for some cases in the lowest frequency range. So thank you very much for your attention. I will now be available for questions.